Take your seats, please. All right, to start next, we've got our first runtime talk today. This one from Dmitry. Okay. All right, I'm going to hand it over to Dmitry. I think we got enough people in here. All right, go ahead.
Is the time ticking, right? All right, so good day, everyone. And I'm Dmitry Olshansky. You probably know me if you use some regex somewhere in D. And basically, I got this title of regex guy, and I hate it. So this is like my step at becoming something else guy. And when I presented this to my friend, his first question was like, unify what? And well, I have to the big context here. And the context is that in D, we don't really embrace like explicit asynchrony, I think. I haven't seen much libraries that do that. And basically, it's all about fibers and threads mostly. And in particular, like the fiber is like an inert thing that you need a thread to drive it. So the fiber is a cooperative user mode thread that you need to schedule manually. We will see some examples of that. And because it is such an inert construct that you need to drive yourself, we have like a number of custom schedulers, which is a nice thing because everybody has the ability to make their own. But it is like a backhanded thing in that everybody has their own and they don't talk to each other very well. So WebD is one, and I think Mecca would be another one, maybe. I haven't seen it. It would, yeah. And Semantic has something like that, I think. So this is like fibers in the most like small number of lines I can get. And the idea here is that we have a binary tree that I inlined, which is super nice to understand. Like, but it is a binary tree of 4 numbers. And we're going to do a post-order iteration of it. And the trick here is that we want to make it like a generator, so that we pull one number, and then we pull another one. And to do that, we need like to do one of 2 things. Like we can call out to something, like a callback, and that would be like exactly the explicit asynchrony stuff. Or we can suspend the execution and then resume it, and this is what fibers is about. So we yield right here, like, yeah, I mean, everybody knows the fibers, right? Like, raise your hand if you don't know what fiber is. I don't. Anymore. All right, so like pretty simple example, right? Maybe, if you see the lines. But, well, when the fibers, like when the rubber hits the road, right? When the fiber gets to the I/O, it looks a bit ugly, because if you were to call a socket, and that would block, it would block the thread. And you have to like yield somewhere in here, but it will be inside of operating system. So you try it like in non-blocking mode. Like if you hit the wall, you like step back a bit, and try another guy who maybe didn't hit a wall on his path, and then another guy. And to do that, it will look roughly like that. So you like read a buffer, and you just check, would that block? Oh, if it did, so I yield here. And I will like continue on and on until I get through. And then I do the same on the right side, because there's like short reads, short writes. And the key here is I need to understand when I should get back to this fiber to do the write and do the read and not hit the wall again. And this is the event loop, basically. Event loop says, OK, this socket is ready. At least it does on POSIX stuff. Windows is completely different, but we'll get there. And, well, there's like an easy solution around it, right? You just wrap everything in your own API. And it's like 2 lines instead of 20. It's nice and clean. And WebD is certainly nice. It's great. And, but there's like a catch here. And a catch here, if you have your own API, there's this little caveat in the yellow color, so to speak, is that like there's 0 C, C++, Rust, what have you libraries that know about WebD. So they don't know how to talk to our fibers, and they will block your thread. And to like add injury to insult, std.net curl, like standard library, right? Doesn't work with that. Socket, no, doesn't. std process, no. std concurrency, maybe. I think Wiped has some integration with it. Some integration, okay. And yeah, but the question I have here is to like faberize the world or not. And like getting to the previous talk here, like Andrei doesn't want magic, and I do. So if you want magic, come to me, we will do something about it. And the magic I wanted is like transparent, I call it like transparent fiber scheduler. And the idea here is that I don't need to do anything, I just import something. It somehow makes C++ code respect my fibers, not block anything, and like profit. And it should be multi-threaded because, well, I don't know, number of cores keep rising up, and megahertz doesn't. And I want to like not stop at this, like it is a compatibility layer, right? Like what is the first one? And and I want to look like beyond I/O and see like what we can do about events, channels, and like good DAPIs for this kind of thing, like minimal one. And here's like example of a library that I'm like making, and it's called Photon, by the way. And I think it's like two names, like 2 times mentioned, so better not forget about it. And basically, what I do is that like import one thing here. And unfortunately, I call initialize here because I was too lazy to make lazy initialization. And yeah, you call like run event loop. And the rest look like the normal threaded code. So I do spawn, and it is essentially like spawning your thread, but fiber instead on a scheduler. And here where I do run it across multiple cores. And once all fibers run out of steam, it will like pass to the next line. Well, we stop the stopwatch and we, like see how much time does it take. And it is basically parallel download of a number of URLs. And it is HTTPS to make it more like complicated. And like some results here. And I tried this like sequentially with threads and with fibers on top of Photon. And the timings are like shit. I mean, it's internet, right? So, well, it is like, you should look at the order of magnitude, basically. And they're flaky. But the idea here, like sequential is roughly 16 seconds, and with threads like 5 something, and with fibers like almost 6, but well, it's the same order of stuff. And well, if you keep running it, you can like switch them around. So sometimes threads faster, sometimes fibers faster. It's not the schedule here. So the idea here is we are at the same speed of threads, and it is a standard library, and it works. And this was like the whole point. And it even works if we don't have multiple cores in this case, because it is I/O bound. And when I got this to work, it felt like this, like something converges, and it didn't blow up on the like after a couple of weeks of segfault, segfault, segfault. All right, and how exactly do we like do this magic? Because well, every magician has his tricks, and here's a mine. Fiber yield needs to happen at system call level, right? So what we need to do is we need to plant ourselves super deep to interrupt right before the system calls. And one way to do it is to like hook into like libc syscall wrapper, because everybody calls that. And that's what we do on POSIX operating systems, like on Linux, because well, I haven't handled the BSD, but there's a super nice event loop here. And this is basically some excerpt of what I have in Photon. And basically, that's all you need to do. Like put a shared library that has a read syscall, for instance. Like you don't even need to match the arguments, basically, because it's all mangling. But you better would match them. And of course, it's D, so we have this funky template with maybe 5 arguments, because all syscalls are pretty much the same if you want to intercept them. So there's a bit of like switching between styles of doing it. And basically somebody in the C world calls it, and it gets to our like intercept. And if you are like this line reads like current fiber is null, basically, are we inside of scheduler? Oh, we're not, so pass through this guy. And like append this horrible error now so that the C doesn't P itself. And then there's this like the D magic if it's inside the scheduler. And I wanted to show like the code for the magic, but the pictures are a bit better, I think, so we'll stick to pictures. Well, a little bit of how layer overview. So it is basically a thread per core model, and all of the IO state is statically memory mapped. So it's kind of pay as you go. So like a memory maps the whole range of available descriptors. And if you use like 100, you don't pay for the rest like a million if you have such a limit. So it is kind of nice in this way. Not much of GC there. And it is like cowboy style log-free scheduler because, well, I wanted to see how fast it could possibly go and what overheads are. And it started nicely, but it got really tangled up at some point. We will see that. And well, there's like it is a research code quality, right? So like super pre-alpha code. And let's talk a little bit about how scheduler looks like. So this is like the first prototype, and I had this idea that I could make everything like symmetric. So I had like typical machine is 3 cores, right? So like 3 threads running on each on its core, and they like pick fibers from the queues and run them. But the moment somebody runs out of work, it goes to the event loop. Like, you are the fastest one, go pick some more work. It gets to the event loop, fetches some more events, pushes them to the work queue of others, and they go. I mean, it was beautiful, but it is like 10 times slower on a virtual machine. Because, I don't know, really. I mean, on real hardware, it seems to work pretty well. On a cloud machine, it sucks through the roof. And I guess there's something about syscalls not being equal on different environments. So I guess this like racy idea of jumping here, maybe not so nice. And they have the fact that scheduler basically waits on 2 things. It's like this one, or maybe this one. Where should I go? Like a 2 haystacks of good stuff, and it's like, oh. So I basically switched to this because I was in a hurry. And so we have like a separate thread that runs on any core. And this one is like dedicated. And the idea is the same here. So like the moment this core like runs out of steam, it will be like preempted. And with a round trip to an operating system of sorts, we get here and we like do the work. And this looks mostly the same on the real hardware. And it works nice on the cloud hardware. So like the takeaway here is like try different environments and see what happens because you never know. Like it works on my machine, doesn't work anywhere else. A little bit about IO state, but I guess it is really involved, but maybe. Well, the thing is, we don't really know when somebody starts using a file descriptor. So it is initially like not initialized. Somebody does the syscall somewhere. So we look like, is it something we already know? No, it's not. Let's start initializing it. But because it's all sort of log-free, we move to a separate state so that the next guy trying to like cast it this way will have to wait and will be waked up later. And similarly, like atomic transitions to like 2 kind of states. And this one is not implemented, but anyway, it is a good idea, and we will get there. Basically, you have like some good file descriptors like sockets, and they can be non-blocking, and you have files and stuff on Linux that don't behave like that. So like two forks in the road here. And the reason we like stick to the thread pool here is that you don't really want to block on a file because operating system thinks that blocking read from a file is a good thing until you miss your file cache, like buffering cache, because then we will touch the disk and then the fiber will hiccup here. So it got to be offloaded somewhere, and it's not only files. So just a good fallback here to not block our nice scheduler that like tries to run through all of the fibers at top speed here. And another messy diagram. It is like a virtue of Linux epoll, really. Like, you start like in some empty state. Like, this is a read side of a socket, and we like keep a state of what's in there and is it ready or not. So the good path is this one. Like, it starts empty. Event loop finds event and goes to ready. Scheduler like wake ups because we scheduled it and does the reading. It goes to empty. It's nice. And it goes in this happy cycle. But then you have the nicety of what if you read like the whole buffer. And on Linux, there's no way to tell if you read everything or not. So you have this kind of uncertain state. So maybe there is something or maybe not. And from there, you can get here and then back to empty. Or event loop finds this guy and says, oh no, there's another event. It must be ready. And there's like this awful mess here. So, yeah. Hope you don't get to implement it at home. Really like tightly packed stuff here. I mean, what was I thinking here? All right. Well, the idea is that like the most complicated thing is like implementing multiplexing, because it's like feels you like it feels like you're a kernel, but you don't have anything to work with. So you have to implement a poll system call without any like direct access to sockets. And what I do is like I have these states for file descriptors, and I kind of put some boxes here that point to the fiber that will eventually get scheduled. And so we have like waiting on 2 file descriptors here. And one event comes in, and we need to like atomically steal this guy, because event loop keeps moving on, but that fiber was already scheduled somewhere. So somebody is running it. And if we like keep it here as well, we will schedule it twice. So that's why there's so many indirections. It's so fun to implement this stuff. And while I was like drawing this, I found that I had a bug in implementation, but who cares? Like, but well, it's all nice and it works on Linux. And then I had this fateful discussion with Walter, because we like it was like hidden research project. And he was like, oh, it sounds nice, and yeah, syscall intercept, great idea, strange nobody does that. But what about Windows? I was like, well, yeah, you can intercept all of 10,000 something API entry points here. But I was once a Windows guy, like low-level Windows guy, so I know about this strange, wonky thing that is called user mode scheduling. And if you read the docs, it says basically this in about 2.5 pages. Like, it is a kernel-assisted support for user mode threads. Like fits the bill nicely. And like the rest, pack of slides. Like, I wish I could like get this device to wipe your memory, because you cannot like unlearn it. But let's see it. Let's see it in action. And the idea here is that Inti guys decided that there's not a problem with threads. Threads are fine. The scheduling them is not fine. Like having thousands of threads come into the kernel scheduler, it tries to do a good job. It tries to pick the right one. But it has like 0 information to pick which one is right. It has some heuristics about I.O., like the guy that completed I.O. seriously should have some work to do. And stuff like that. It's low voodoo and trying to like throw their bones and see which one is the good one. And throwing balls takes time. And the idea here is that we get the threads that is not scheduled. It's just like sitting there. And we like pick a number of heroes that will run those threads, like the guys that will schedule them. And what we get in the return is that operating system will automatically switch to the scheduler if something blocks. And it even will schedule you away if you page fault. And this is something that Linux doesn't do. So this is like super powerful here. because it means you're unstoppable. like even if you get to touch some bad stuff, it will be bumped outside of it. And what nobody knows is that the TLS problem is solved because it is a real thread and it had TLS. So to the point, it is solved problem here. And a bit of how it works, and I'm like a poor artist here. Like boxes are talking to boxes. Yeah. Yeah. Yeah.
Okay. The page fault point you pointed out needs to be, people need to be aware of it.
Yeah.
Because when you work with fibers, you allow yourself to assume there's no preemption.
Yeah.
And that works as long as you do I/O-based switching, because you know when you're doing I/O. But if you might switch on page fault, then that's effectively preemption.
Yeah, it is.
It may happen at any time. So people need to be aware of that when they write their code.
Yeah.
It's not transparent.
It is a bit not. Yeah. I mean, well, if you say page fault, it's like you are level deep there. So if you know page fault, you're already like at this level of detail. So I mean, it is nice to have ability to do preemption here instead of blocking your thread. Well, but we'll talk about it later. I mean, so the idea here is that like we have kernel threads and user mode threads, and they like one-to-one, and yeah. There's like your MSR in the kernel doing your dirty work. And what they decided to do is like, we can switch those guys without switching those guys. And if nobody notices, it is good. Like we keep switching them. And eventually we do a system call. And we are on our own user mode thread here. So like in T-kernel, like we'll swap it back and restore sanity. And it will like be off to work here. And user mode thread is like somewhere on the side, like waiting for. And we get to like run the other guy that was sitting there, like UT2, and it's here. And after a while, that guy completed his work, and we get like completion here, and we get it back, and we can switch again to it. So this is like the kernel side of things. The good news is like you can switch yourself between all of those threads. Really, without going into the kernel. That's the point, actually, not the page fault. Well, we'll talk about it. Well, but it's not all roses, right? Like, if anything ever was roses with Windows. And the thing here is like there's perfect documentation on the subject, like API documentation that says nothing about how you would combine it. And there's like one interview with Windows kernel architect that draws some funny things on the whiteboard, but it doesn't go into how do you write code for it. There was once nice demo at Build conference, I think. And this is how I remember it, because it was like a fun, low-level thing back into some year when Windows 8 came out. And there are like 2 examples on the whole internet that try to do it. And my like biggest joy was that none of 2 examples and my code that I wrote worked on my virtual machine. And I was like, well, sucks. And I found this like forum post, oh, maybe it is deprecated. I mean, it was so close. And I found this strange guy who is maybe reverse engineer. And basically, I will just quote it. And a few months ago, I found that kernel began to enforce usage of, what's that? Like CR4FG save-based feature in order to allow usage of user mode scheduling. That's a good find, yeah? And turns out like VirtualBox messes with CPU flags and doesn't propagate to operating system those. So, all right, pick the right VM, I guess. And here's a link if you want to try UMS and not fall in this pitfall. Well, closing thoughts on this. It's been a long time about Windows, and yeah. Well, the idea here is that while you can get this user mode preemption, it is actually a bit like the kernel one, just with a bit more hoops. So you have to do asynchronous I/O anyway. So what I do is use the same strategy to override some of WinSock functions, especially like receive, send, and I do overlap I/O with completion ports instead. And it is really nice since that the Windows version was like 2 times smaller than the Linux one, and it is kind of interesting. Well, there's some other interesting issues here that you could use some low-level APIs from Windows as well to like speed up it, maybe, if you get to like have fun with system calls that you override, maybe as well make it nicer and faster. And thread is a thread, so like spawning lots of them is still more costly than the fibers we have. And it's not the same as a fiber in many ways. So it's why I thought about like unifying stuff and maybe not calling it a fiber, but some kind of user mod thread or light thread of sorts. And the whole thing, of course, is 64-bit only recent CPUs, so not everybody gets to play with this stuff. Thankfully, I do. Okay, let's get back to the real world. And people love HTTP for no apparent reason. And fast HTTP is not the main point of Photon. Like, I don't want to implement HTTP servers ever. I don't want it. But I need to show something, so I pick a Node.js HTTP parser, the C library, and I use plain std socket to prove the point that you don't need anything special. And I do some sensible performance optimizations, but then I look at competition and they do some crazy stuff, and I say, like, if they do it, there is no shame in it, so I do it as well, and a bit more of it. And my favorite one is HTTP server has to return a date string. And with our facilities for it, like calling to the timer, to the clock, formatting the string, it turns out like in a hello world kind of benchmark, it's maybe 20-something% of the overall stuff. So what they do, they spawn a super slow thread that sometimes wakes up, like writes the new date in there, and everybody's like, hey dude, thank you, we will use that date from now on and for the second to come. And yeah, he's like, well done, and gets back to sleep. And we do that, because it is nice and we get super high on the benchmark. Anyway, a bit of code, and I tried to make it bigger, but it doesn't fit anyway. But it is like straightforward stuff. You just use the TCP socket, like accept. It does no error handling. It is guilty as charged. But well, it is simple. And the threaded one is about the same except for 3 lines. So it is exactly the same. Yeah. Like, I guess the main is the only one, but yeah, spawn instead of what it was, like new thread and start. And yeah, new fiber start, spawn server, start loop. Just to like, and then the HTTP server itself is this funny thing. It's just a wrapper on top of ungodly C library that does it with callbacks. And I'm taking DMD to the gunfight. So it's all compiled on DMD, like the proper compiler for benchmarks and shaming people. And I picked some top guns from Tech and Power benchmark, just for fun. And I'm trying to benchmark threads versus fibers. And this is like threads versus fibers. And I tried to pick the right colors, but anyway, like the red one is like requests per second by Photon. And there's like concurrency, we're bumping it up. So you need a bit of concurrency to get to like saturation point. And just keep dancing here and for no apparent reason because it is like super noisy anyway. And gets slower down, of course. And this is like latency for this guy. And it keeps going up to like 200 milliseconds, something. And this is like all the virtual environment because I wanted like to be closer to production people usually have these days. And this is like threads, and it looks nice in the RPS. I mean, why would you care about fibers or just use threads? Nice, fast, it's okay. But then like you look at latency and like, oh shit, what is that? It gets closer to a second. Well, and let's go for DMD versus everybody else. And I picked like the fast HTTP, which had like the proper speed hacks that I have. And Undertow from Java, it's actually like super fast server, and I was benchmarking against this one because I haven't found anything faster. So Java rocks. And so the threads, the Photon, and Go, and like Java. And here's like latency of everybody, and we're like in the same ballpark as everybody else, except for threads that are go insane. And here's like the memory used, and like no miracle here. Like Java uses a bit of memory, a little bit. And threads are about 2 times costly then. But important thing, like don't take it for real. Just don't trust any benchmark at all. It's just to show something, not much beyond that. And yeah, I think that's the end of the benchmark stuff. All right. So we're getting to like things beyond I/O, and we're like getting to like things that are not really done yet, in any like good measure of done. And the thing here is like channels and communication by like synchronization by communication, like favorite pattern of certain language that I will not name. And if you like look at it from the D side, like what's about it is just some kind of thing that has like output range interface and put range interface, and maybe some kind of thing to wait on it. And that's it. I mean, this is a channel. And yeah, I'm just labeling the obvious in the D terms. And all of that will work as long as, I mean, what's wrong about it if I want to make it like multiple producers, multiple consumers queue? Like any guesses? Like, what would on this picture break if I will make it like multiple consumers here, like this abstraction of having output range and input range of it? What we have multiple consumers? What goes wrong? Nope, that's not the problem. Like, imagine the range interface again, the input range. Yeah, but we were talking about it, right? So yeah, Sonky just cheated because I was discussing this with him a few days back. And the idea here is that if you are trying to have multiple consumers here, somebody like gets, oh, is it empty? Oh, it's not. So I like take the front of it. And somebody else was doing the same, but it popped it. So you go there and you take nothing. Like, and you probably take fault or something. Or maybe worse. So this idea is like for MPSCQ. And I don't feel bad about it because if you look at some actor systems, they basically MP multiple producer single consumer queues because actor has like a mailbox. And it is essentially a queue that gives you messages from everybody. So it is exactly like this thing with a new name. Yeah, so to speak. And like a little bit of inventing the API here. Like we need some kind of stuff to wait on, and it must work across threads and fibers transparently. Again, I'm for magic. And the idea here is that all we need is like a couple of primitives. I'm not set yet on the kind of primitives. I don't like those two, especially there are 2 of them. Like, well, event is fine, but we will see more about it later. And this like the magic of the event loop is to like wait on a bunch of events. Yeah. So this is like my imagination of what it looks like to join STD algorithm with like channels, events, and stuff. And the idea here is that like some ranges define ready and define events that you can wait on. So if you have a multiple of those, you can do your map filter and stuff, and you get like a queue of T, and you map it to a queue of U, and so on. As long as your algorithms propagate the asynchronous state here. And reason for that is multiplexing. That is not on this slide, but The idea here is that we can have composable stuff for one. And I think the biggest issue with certain languages that shall still remain unnamed is composability. Like channels are super low-level API actually. And if you have no way to abstract away common communication patterns, it is a net loss. You better stick to actors, to message passing explicitly. But in D, we have like plenty of compile time stuff, plenty of algorithms, wrappers, and retro stuff. I think it should be combined, and I would want help on that because it takes a lot of thinking to get it right. And maybe it will be like a couple iterations on this concept. But I believe there's like super great synergy between ranges and channels. And we think we should capitalize on that. It's all wobbly, I know. Bright future of Photon is that the basic stuff is done. It's sort of fast. It is a bit loose. And I want to fix a lot of bugs there. But, well, I want to go next. And next is multiplexing and composability. And communication between all those fibers in some way. I think maybe about this one. Photon should not care about user-land things. It should be there at the most common layer down there. And the rest would easily be done on top. That was the point. And of course, more syscalls to cover, and maybe we need some kind of executors, really. And we may even blend the distinction between is it thread, is it fiber? Well, it is something that I want with preemption. Okay, it's going to be thread. Or if it's something that will be cooperative, okay, it will be fiber. If it's something Windows supports both of those, so should fit well. And help wanted. I mean, I really need it at this point of time, because there's a ton of things to test. And you may not like Windows, so I'm not expecting anybody to help me here. But there's 32-bit Linux for somebody who cares. FreeBSD, I know a lot of, not a lot, but small group of people really care about it. macOS, obviously. Better C. Well, better C, it feels like it should be there somewhere. You pick your C program and you add the D fibers in there and nobody notices. That's really thought. If fibers were better C compatible, nobody would notice it. You just swap the new pthread create with some other thing. And you cheated on them and it works nice and it's super fast and everybody's happy. It is like a joke here. Well, here's a link and it's it. This is it. I hope for questions because no matter how much of stuff I put on a slide, it doesn't really cover things. So, thank you.
When you call run fibers in the example, is that needed for the fibers to actually run, or is that just a synchronization primitive to join?
All right, run fibers basically start the scheduler on this thread and spawn as many more as I have cores at the moment. And well, at this point, everything starts. You can keep spawning them afterwards.
Okay.
But you have the primer here that says, okay, I did all things I need to do before I get into this nice fiber world, and let's start.
Okay.
But you can spawn threads as well. So
I just think it'd be nice if it were just as easy to use as in that language you keep not referring to.
I think the start call is a misnomer because it was easily removed with lazy initialization. The last one is a bit more funky. And getting back all the way back, all the way. There's keyword there that somebody was joking about in the runtime here. And the idea was that run fibers will be in the runtime. And your main will be a fiber. But you will not know about it. And people will certainly burn me on a
No, sounds awesome.
Yeah, I mean they will put me to the stake and burn it. Because it is magic, squared.
Any other questions?
So I played around with this idea a few years ago. It's quite nice and quite obvious to do a lot of things. How do you think, how well will we be able to cover all libc APIs? Or is there maybe you found a way to catch them on a higher syscall level to interrupt really the syscalls? Because obviously also other languages like Go and Rust do their own syscall wrappers and don't use libc nowadays.
Not always, yeah. Well, the thing about Go is you want to use Go, it has garbage collector, and it's like two titans that will fight against each other, like D garbage collector and Go garbage collector, and you can ask Ethan how nice it is. And getting back to C and C++ and Rust, well, this thing is not like 100% solution. Like, it will be super strange to declare things like that. Because for one thing, you want to control blocking or non-blocking if you like super low level here anyway. For another thing, there are some syscalls that basically you cannot implement in all of the quirks that operating system has there exactly like it is. So it is like a solution for common things. Like for instance, if you take like a C++ server and you try to hook it onto this thing, you better not do it because they have a deep control over what they do in the server side usually. On the client side, it is more brighter and more simpler because they want to cater to languages like Python, PHP, and they are like most of them like single-threaded and simple. And that's where we can like capitalize on this stuff. Speaking of syscall like layer here, well, the idea is that worst case we can fall back to a thread pool on the side. Like if you have no idea how to make it non-blocking, like put it somewhere and let like a bit of latency here, but you save the latency for everybody else on this thread, so maybe it's a good trade-off. What else? libc syscall wrapper is a little big. Like I looked at all the kernel syscalls, there's plenty of them. There's maybe like, I don't know, 30, so to speak of, that are really important ones. Like mostly IO, it's like maybe 12, 20 syscalls. So the Windows stuff is like really interesting to me. Well, when I like got past all of the obstacles, it looks like a very powerful thing here. But it has like a number of caveats that I don't totally understand yet. It is black magic, and Windows guys use it in SQL Server that you maybe heard about, right? And there is a reason for that. So, like, but problem with it is like some way, like a secret that you put on top of your table, like right in the room full of people, and nobody notices. Like some kind of like secret that nobody wants to touch. It's there. It's kind of public, but nobody can use it. Mostly like that. And yeah, I hope they like keep it. And I guess they will as long as SQL Server works. So that's like our insurance here. Well, I kind of let loose here. So next question.
No more questions? Okay, thank you, Dmitry.
Yeah, thanks.
All right, everybody go ahead and take a 10-minute break, and we'll come back for our last talk before lunch.